Thank you. So, dear colleagues, I'm Julián Tomaštík from Technical University in Zvolen, Slovakia, and I feel a bit like a stranger here because I do not know much about laser scanning photogrammetry. I'm not even a forest ecologist, but I focus on positioning, especially under forest canopy. I think that in the current era of multi-source data, we often face the challenge to collocate the data, which is quite a difficult task. We can see the two main approaches to do this, to do the, I mean the absolute positioning. We can use the ground control points, or a bit newer approach is the direct georeferencing, where the camera locations are directly positioned, especially using GNSS. With the GNSS evolution in the last few years, there are few characteristics which grown quite significantly in comparison with the beginning. 25 satellites. We now have more than 130 satellites. We have more civil signals. And from practical point of view, there is a decrease in receivers' dimensions and in their costs. So in our research, we want to use these benefits, and we focus mainly on the low-cost solutions. So why the low cost? From my point of view, there are mainly two basic constraints when adopting some method in the practice, and this is often the high price and complicated methodology. So we want to mitigate at least the one. More specifically, we tested raw measurements available on Android devices. This is quite a new feature, providing opportunities to process the GNSS signal like the signals from higher level devices. And there, and then also a standalone receivers. On the picture, there is a receiver built on U-Block's F9P evaluation kit, around 300 euros. Perhaps the first wooden GPS, so it can swim, it can burn, so an ultimate survival device. Jokes aside, we have done some preliminary testing in our university campus on 3 points. This was a static measurements for 20 minutes, 10 measurements under lift on, and 10 measurements under lift off conditions. I know that this is not a forest, but the conditions under partial and full canopy were quite challenging also for a geodetic GNSS receiver. Just a small overview of signal quality. On the upper pictures you can see the signal from tracked satellites. Those red ticks are cycle slips, so discontinuities in phase measurements, which are crucial for the highest accuracy application. So here we can see that the smartphone is far beyond the standalone receiver, and also the signal-to-noise density around 10 decibels per hertz increase for the standalone receiver. With regards to the accuracy, we find out that the data from low-cost receivers are very sensible on the software, because most of the professional softwares cannot work with data of such low quality. So we use RTK Leap, free open access software, and I'm happy that we directly collaborate with Team Everett, who is developing an adaptation of RTK Leap for low-cost receivers. There was a site link. I don't know why we cannot see it. RTK Leap Explorer, if you want. Here you can see the outputs from Pixel 5 from smartphone. So on open area, the results are quite promising. Under 1 meter under canopy, it is not a big win, but you can see the difference. The blue is the original RTK Leap code, and orange is the adapted RTK Leap code. Perhaps not as visible here, but here are the results for the u-blox 9P receiver, which even under the worst conditions achieved results or achieved accuracy under 10 centimeters. So those are results of static measurements, perhaps applicable for GCP approach. The other branch we are working on is direct georeferencing of terrestrial photogrammetry. This follows our paper of UAV direct georeferencing when we achieved accuracies of under 10 centimeters for a 300 hectares plot. Also here we work with low-cost receiver, the MLIT Reach M Plus, which is also built on the F9P chipset. These are a bit preliminary results, but here it is shown for the open area. The red crosses are the reference. The green dots are camera positions. Mean camera error provided by Agisoft was 24 centimeters, but all solutions were fixed, so ideal. Under canopy, the solutions were to float, but the mean camera error, it's not so bad either, 40 centimeters. In this case, we plan to filter these positions based on e.g. Standard deviations, which are reported in the outputs, or based on the camera errors reported in photogrammetric software, because we do not need all the position to georeference the outputs. We also work with some combination, which some of them were already mentioned, the simultaneous localization and mapping works with computer vision, inertial measurements, gyroscopes, and accelerometers can be used, for example, also with smartphones, but you still need the basic source of the global coordinates, because in principle these methods work in local coordinates. So no general conclusions so far, but I just want to encourage you to give a chance also these low-cost solutions, and perhaps together we can increase the efficiency through the decrease of costs of data acquisition and devices needed. Thank you.
Thank you, Julián, for your presentation. Are there any questions from the audience already? There is a question in the back.
Your more practical question, what's your experience, what people in forestry expect from GNSS devices in terms of accuracy? Because my feeling is that usually people think that the accuracy is much better than it really is.
Yeah, this is, I think, quite a complicated answer, because first we need to declare what accuracy we need objectively, and then somehow give it to people. As you said, there are quite extremes in the practice. Some one part over-evaluates the GNSS, and another thinks that it is absolutely not usable. So I think that this is one of the reasons why the research is needed, to give them some objective numbers, and then they must decide if it's not good or good enough.
Thank you. I have one technical question. The paper you showed at the end from Julka Huda, which was used for SLAM positional accuracy. I have it. Sorry, I didn't read the paper yet, but SLAM is known that you have to go and come back to the same place.
Yes,
is it necessary?
You need to do the loop closure.
So you need to go and come back, and then you kind of recover.
It works also without the loop closure, but when you do the loop, you can mitigate the misalignment. Mm-hmm. So you can go straight line, but you don't know what is the error at the end.
Okay. Mm-hmm. Thank you.
I have just one additional comment to these accuracy issues. I have the feeling that people often don't understand the difference between the measurement accuracies, between the measurements and the absolute accuracies. And I think this is the biggest problem, because on the device they see the difference between the individual measurements, and then they think, okay, this is my absolute accuracy.
Thank you all for your questions and comments. I think it's time that we move on to the next presenter.
Thank you.